Good afternoon. My name is Dwayne Brown with the Office of Communications, and welcome to NASA headquarters. Today, NASA reveals near-Earth asteroid findings and implications for future research from the agency's Near-Earth Object Wide Field Infrared Survey Explorer, in short, NEOWISE. Today's information and graphics can be obtained on the web at www.nasa.gov/WISE. We will have brief presentations from our presenters, then open it up for questions at our NASA centers and the phone bridge. Before we get started, let me introduce you to today's speakers. First up, Lindley Johnson, NEO Program Executive, NASA Headquarters, Washington. Amy Mainzer, NEOWISE Principal Investigator, NASA's Jet Propulsion Laboratory, Pasadena, California. Tim Spar, Director, Minor Planet Center, Smithsonian Astrophysical Observatory, Cambridge, Massachusetts. And Lucy McFadden, Scientist, NASA's Goddard Space Flight Center in Greenbelt, Maryland. And with that, I'll toss it to Lindley to start us off.
Thanks, Dwayne. Thank you all for tuning in to hear about our progress with the Near-Earth Object Observation Program. We're here today to provide an update of our understanding of the near-Earth asteroid population and announce achievement of some significant goals in finding our nearest neighbors in the solar system. Over the past 12 years, our work to find near-Earth asteroids has largely been done by several ground-based observatory teams. But in 2010, NASA augmented those efforts by enhancement of the ground processing of the data being returned by the Wide Field Infrared Survey Explorer. This enhancement project, called NEOWISE, processed all the sky images sent back from WISE to detect objects moving across the sky background, those objects that would be in our solar system. This was mainly done to find near-Earth asteroids and comets, but a great many main belt asteroids and other objects in the solar system were also found. The year of WISE observation also led to two very significant findings for the near-Earth object observation business. The NEOWISE project has confirmed completion of the original goal set with Congress back in 1998 of our program, which was to find 90% of the 1 kilometer and larger near-Earth asteroids. The second significant finding is the population of medium-sized near-Earth asteroids, those between 100 meters and 1 kilometer in size, is probably somewhat less than we were estimating before. So if I could have the first graphic up. This is an animated view of our solar system looking down from the sun with the inner planets' orbits depicted as circles. Mercury, Venus, Earth, and Mars as the outer ring. I have to point out that this diagram, the sizes of these objects is not to scale. If it were, even the planets would be so small that you couldn't really see them. So if we could have the animation in motion now, all the small red dots seemingly swirling about like gnats in their orbits about the sun are shown in the red. Those that we previously knew about are now shown in yellow or maybe orange in some screens. Those that were detected by the NEOWISE project are now in blue, and the new objects that were detected by NEOWISE are now shown in white. From this sample that the NEOWISE project was able to find, we've projected a more accurate model of the overall population that is over 40% less in numbers, which we now compare here with the old model of the estimated population. So you can see considerably less numbers. So if this new model holds up, it will mean the number of 100-meter and larger near-Earth asteroids yet to be found is somewhat less. But even this new population, there are over 15,000 objects still to be found. It will take more capable systems and several more years of survey efforts to find these relatively small and dim objects. It's something like trying to detect a candle at the distance of the moon. To tell us more about the NEOWISE project is our principal investigator, Dr. Amy Mainzer.
Well, thanks, Lindley, and thanks all of you for tuning in this afternoon. It's great to be here. WISE was a very short mission, and we're very happy to have these results to present so quickly. So as Lindley mentioned, we find that there are fewer near-Earth asteroids out there. However, it's very important to note that fewer does not mean none. And there are still tens of thousands that are out there that we need to find, that are left. As one of my colleagues at the Jet Propulsion Laboratory likes to say, the best 3 ways of dealing with the potential of an asteroid impact are to find them early, and find them early. If you can find near-Earth asteroids when they're far away, it would take far less energy to mitigate a potentially threatening object. So this is why we carry out surveys like the ones that Lindley has described, and like NEOWISE. So one of the characteristics of NEOWISE is that it really was a fairly small telescope in a low Earth orbit. In fact, the telescope would kind of fit under your arm like this, so it's not particularly large. But by virtue of being in space and operating at infrared wavelengths, it's a very powerful telescope, and it turns out to be very good at finding asteroids and comets. Now, if you go to the first animation here, you can see a little representation of what WISE looks like going around the Earth. It's always pointing outward from the Earth, surveying the whole sky, and as the Earth goes around the Sun, this allows the telescope to very quickly and efficiently carry out a survey of the whole sky. And in fact, it was so fast we were able to survey the whole sky twice in infrared wavelengths in only 1 year. And you can see here a little representation of the difference between visible light and the infrared light that WISE was able to see. So this was a very efficient and effective way of surveying the sky. And the original purpose of the mission was actually to study cool stars in very distant galaxies, and it's doing a great job of that. However, it turns out to also be very good at detecting asteroids. This is because it's using infrared light. If we look at the next slide here, we can see 2 asteroids. We can see a close-up of them. One is very bright and kind of shiny, more reflective, and the other one is very dark, like a piece of charcoal or barbecue soot at the bottom of your barbecue. They're both the same size, however. Now, when we're close up to these asteroids, you can actually see that they're the same size. But the problem is, most of the time, we're not close up to the asteroids. If we roll the animation, we can start to see what happens next. When we're close up, it's easy to get a very good estimate of their sizes, but now imagine that they're far away and we're observing them through a very distant telescope. Even if they're at the same distance, to this visible light telescope, the one that is brighter is going to appear brighter to the visible light telescope, and the one that's darker looks fainter. However, if we can look with an infrared telescope, what we're seeing now is actually heat that's being emitted from the objects. And so to the infrared telescope, they look the same brightness. And from that, we're able to determine their sizes. The other benefit of this is it means that infrared telescopes are less intrinsically biased against finding small, dark near-Earth asteroids. And this gives us a better representative sample of the true population. So with NEOWISE, we didn't go out and find every single asteroid that's out there, but we got a good representative sample, kind of like doing a census, where you take a poll of a small subset of people that you think is representative of what everybody thinks. And so that's what we've been able to do with NEOWISE. If we go to our next chart, we can see how these results have applied. If we look at the very largest asteroids, these are 1 kilometer and larger objects. So these are the planet busters. These are the things that are like the one that is thought to have caused the extinction of the dinosaurs. The good news here is that with NEOWISE, we've been able to confirm that the worldwide community of astronomers, both amateur and professional, all over the place, have now found more than 90% of all of these really big asteroids. And that's represented as the filled-in asteroids, the ones that look sort of tan. We believe that there are something like 981 in the total population. And this is very close to the original estimate of about 1,000 objects. That's what you see in the blue outline right there. The green outline represents the difference in our prediction with NEOWISE. So we're saying the total number is about the same, but the new thing here is that we can now confirm that we have met the so-called SpaceGuard goal of finding 90% of all the 1 kilometer asteroids. So we know where they are, and by virtue of the fact that we know these objects and we know their orbits, we can predict that they are no longer hazardous to Earth, in the sense that we can follow them, and we know that there are none that pose any imminent risk of an impact. If we look at smaller sizes with the NEOWISE data, if we go to the next line in the chart, you can start to see the differences in the previous prediction of the population versus our prediction of the population. The previous prediction is shown as the blue outlines, and our prediction is shown as the green outlines. And again, you can see that the fraction of objects that have already been discovered are shown as filled in. And going to still smaller sizes, we can see another layer of this. So if we could have the next layer in the chart, you can see that now the prediction is showing that there are somewhat less, but we've also found proportionally less of these objects. So there are still many remaining to be found. And if we go to the next layer, you can see that this continues. So if we go to the final layer of the chart, for objects that are smaller than about 100 meters, the NEOWISE survey is not really able to comment because we just didn't see very many objects that are that small. So we're not able to comment. However, previous studies indicate that there may be as many as about 1 million or so of these very small asteroids. But even so, if we sum up and look at all of these things, everything between 100 meters and 1,000 meters, 1 kilometer, we believe that there's something like 19,500 predicted to exist in the total population, compared to a previous estimate of about 35,000. So there are fewer. However, it's important to note that we've only found a fairly small fraction of these to date. Okay, so to give us a little bit more information about infrared and the value of these surveys is Tim Spar. Dr. Tim Spar is the director of the Minor Planet Center in Massachusetts.
Thanks for the lead-in, Amy. The job of the Minor Planet Center is to collect all of the asteroid data that's taken worldwide. And so we're in a position where we interact with all the other asteroid astronomers. We collect positional data. We distribute the orbits. And one of the things that we do is to try to discriminate between near-Earth asteroids and the main belt asteroids. And from this perspective, from my perspective at the MPC, the NEOWISE mission is the most important project in my career. And the real punchline of this is that they observed the size. They were able to determine the size of every object that they observed. In addition, when I combined the positional information that they gave us with that from the other surveys that Lindley described, they were able to produce a very good orbit model for all of the objects, and not just the near-Earth objects. I'm talking about the main belt asteroids, the group between Mars and Jupiter. NEOWISE observed actually 25% of the entire known asteroid population. So that was something like 150,000 objects. And because they could, again, because they could determine the size of all of these objects, we were able to put together a really good model. And it's important to know that this was something that was a contributory effect. This fit in perfectly with the other surveys that are already there. It looked at a different wavelength and a different area of the sky, so everything fit together very well. Now, to give a little idea of the census, we've got a video here. And all right, go ahead and start that, please. Each little dot, again, not to scale, is an asteroid that was observed by the NEOWISE program. In the center, you have the sun, and the outer orbit there is the orbit of Jupiter. And if you give that just a good look, you can see the sampling of all the different populations of main belt asteroids. There's objects out by Jupiter, and there's a whole bunch of objects in there near the Earth. So that's the near-Earth asteroid population. And this is showing just over 1 year how powerful this program was. Observed a quarter of the known population and censused a good bunch of the inner solar system. So I would like to give sort of a little information on how the spacecraft works in terms of determining the sizes, and we want to make sure we get this through. So the next picture that we have here is a visible light image. This would be what you would see. Go ahead, cue that one up. All right. That would be what you would see from a visible light telescope like the existing surveys that we have. So you see 3 asteroids that look similar brightness. Now, if we could go to the next iteration, please. So on the left-hand side, we have a small reflective object, and on the right-hand side, we have a large dark object. And again, as we heard before, those will look the same in the visible light. Now, if I could have the last slide, please. This is the real key. In the infrared light, we get a discrimination in the size from NEOWISE. And so on the left-hand side, the smallest object actually looks to be the dimmest in the NEOWISE images, and the right-hand side, the largest object, looks to be the brightest. This is really the most important part of it. If you think of trying to do a census, you need to know the actual physical characteristics of the object, and this is what we get from NEOWISE. We got the actual sizes, and as we take a fraction of the population, we can extend that, knowing the size and the orbit characteristics, to the whole asteroid population. And that, to me, is why it was so important. Now, I would like to hand things over to Dr. Lucy McFadden to drill down into some of the other aspects of the project and other NASA missions.
Thank you, Tim. First of all, I find it really exciting that scientists continue to find things in the solar system, bodies in orbit around the sun, and objects that are close to our backyard in the near-Earth space. I want to congratulate the team for your successes, and I know from experience that in order to conduct a survey and to locate and discover new bodies from spacecraft missions requires a lot of planning, a lot of ingenuity, huge amounts of computing power, and then hours and hours, months of discussions with colleagues and poring over the data to validate the results. So I want to congratulate you all. It was a big team effort that you should all be proud of. There are 28 co-authors on the papers that are to be published, and each one of them has had a critical role in the success of the project. Additionally, it's terrific to have a satellite that can reach the greatest depths of the universe and also find things right here close to home. Can I have the first slide here? Again, we like looking at the bird's eye view of our solar system with the circles, or actually ellipses, representing the paths of the planets, and the white dots representing the asteroids. They're minor planets. We consider them minor planets because of their small size, and it's really fun to welcome the new asteroids into our consciousness of the solar system. Another concept that I marvel at is that their mere presence, reveals the past. When the solar system was forming, solids condensed from the rotating disk of gas and dust, and planets grew, some of them to hundreds of kilometers, and their growth was stopped by the formation of the larger planets, the major planets that are tens of thousands to hundreds of thousands of kilometers in diameter. So in the asteroid population, we see both early planets that grew to what I call a small size, hundreds of kilometers, but also the remnants of larger planets that were broken up from collisions in the solar system. And the challenge is to determine which asteroids are which and what the time scale is, what happened when. So next slide, please. To complement the surveys, what the surveys tell us is what the big population is, give us the big picture. They also allow us to decide which ones to go study up close with robotic missions. So here we have about 9 asteroids that have been studied with robotic spacecraft missions in the past 20 years. We've covered a wide range of sizes and asteroids from different parts of the whole asteroid belt, as well as some in near-Earth space. What I'd like to point out here, the obvious one, the biggest one here, is asteroid 4 Vesta, which has a spacecraft in orbit about it today, orbiting for the next 9 months, and revealing this body as a world of its own, looking at the surface properties, determining its composition, and determining the processes that hit it. And you can see by looking at the surface that there are craters on the surface, and that tells us that there were collisions. Bodies collided with the planet, bodies collided with Vesta, and debris was ejected from it. And over tens of millions of years, or maybe longer, objects have found their way through a dance, and if we could go to the next slide, through a dance of gravity and solar system dynamics, bodies have found their way into collision course with the Earth. And we see these as meteors, mostly, fireballs, terrific fireballs that are spectacular. This one was captured during a football game in 1992, and it traveled the whole length of the eastern seaboard and coincidentally landed in a small town in the Hudson River of upstate New York, where I used to spend my summers. And it landed as a meteorite. So we have in our collection meteorites that have landed on Earth. And as an example here, we're showing a picture of myself on a scientific expedition in 2008 looking for the remnants of an asteroid that was discovered by astronomers with their telescope, who determined that the asteroid was going to collide with Earth, and it broke up in the Earth's atmosphere, just as the Peekskill meteorite did. And through communications and precise calculations and measurements, we were able to determine the location of the meteorite fall and actually travel with students from University of Khartoum and search for these meteorites and recover them. So we have these samples here, which now cosmochemists can study in their laboratories and give us yet more detail on the processes and the history of products and processes in the solar system. So what we've done is going from points of light amidst the infrared glow of the universe to rocks from space that tell us about the solar system's 4.5 billion year existence. And then, instead of just being afraid of asteroid impact disasters, these objects can tell us information about the solar system that we can just marvel at.
Thanks, Lucy, for summing this all up. And just to pull it all together for what we've learned today from the NEOWISE project so far, is today we have good news with some important caveats. So we've learned with NEOWISE that the worldwide community of astronomers looking at near-Earth asteroids have found 93% of all the really big near-Earth asteroids that we think are out there. And this has substantially reduced the risk of an impact that is not warned. In other words, we know now where most of them are and where most of them are going. That really has reduced our risk of an unwarned impact from a really big one. Also, we predict that there are somewhat fewer medium-sized asteroids out there in near-Earth space. But fewer does not mean none, and there are still tens of thousands out there that are left to find. So we still need to keep going on the survey efforts. We have a lot of work left to do, much more research, and we still need to specifically analyze the subset of near-Earth asteroids that get really close to the Earth. But overall, at this point, our understanding of the near-Earth asteroid population has been significantly improved, and we believe that the hazard to the Earth may be somewhat less. Thank you.
All right, thank you all. And now we're going to transition into the question and answer period. We're going to first start down at the Kennedy Space Center, where we have one question and a follow-up, and then we'll go to the phone bridge. Kennedy?
In Florida today. Last April, the President of the United States was down here at Kennedy Space Center, and he challenged NASA to send astronauts to an asteroid by the year 2025. I was wondering if you could tell us whether any of the findings that you found in your survey might produce targets of opportunity for human exploration.
I'll take that. Thanks for the question. This is Lindley. We're working with the human spaceflight folks in examining the known population of near-Earth asteroids to determine if there are available targets. This research, the work that NEOWISE has done, has allowed us to understand the population of these objects much more and to understand where we could find more available targets. But there are a number of things that still need to be done in the survey. The objects that come closest to Earth tend to be the smaller ones in the 100-meter class. And as you see, there's a large percentage of the population still to be found. But the efforts to date have shown us what the population looked like and where we might be able to find and the techniques we need to use to find more of these objects.
Todd, you have a follow-up?
And just as a follow, could you tell us in a general sense for, say, my next-door neighbor, why we would actually want to send human explorers to an asteroid?
Well, exploration of the solar system is one of the goals of NASA and our scientific program. The human spaceflight is a part of that exploration. So it's a natural stepping stone of our exploration into the solar system.
Okay, we're going to transition to the phone lines now. First up is Alan Boyle with MSNBC. Alan?
Thank you. I realize you're focusing on near-Earth asteroids today, but there's been so much talk about the potential for finding a Planet X or some sort of large body through the WISE survey. Can you comment on any status on that sort of search, or maybe even reassure people that Planet X isn't coming to get them next year?
Yes, this is Amy Meinzer. I'm happy to answer this one. Planet X is not coming to get us. But we are looking to see if there are any other bodies in the outer part of the solar system with the WISE data. This is a very natural project for WISE. And so we're still working on it right now. We've obviously just returned a huge amount of data from the telescope that's going to take us a long time to sort through. But the initial results are very promising. You may have seen earlier results where we've discovered a new class of very cool type of stars with WISE. But the search is still on, and we don't think that there's anything that's hazardous in the outer solar system. We think that this is just a sort of if there is something out there, it would be a large body in a roughly circular orbit.
Our next caller, Denise Chow from space.com. Denise?
So when you say the initial results are very promising, the initial results are very promising. Anything else you wanted to say on that point?
We've actually been able to confirm the discovery of 100 new objects that are these very cool stars called brown dwarfs. And so that's very similar to what people are interested in looking for. So we've actually found some of these that are relatively close to the Earth, but none of these are closer at this point than the nearest star to our solar system. So it's a good start, though.
Thank you.
Okay, now we'll go to Denise from space.com. Denise?
Hi, Denise Chow at space.com. Thanks for taking my question. I was under the impression, but please correct me if I'm wrong, that the WISE mission was officially shut down in February of 2011. So does that mean that in the months and years to come, it'll be more of sifting through the survey information that has been collected, or is there a plan to continue with another mission to take more of these sky surveys?
Well, this is Amy, and I'll answer this. We like to think that the WISE spacecraft, having completed its baseline mission successfully, is now in honorable retirement. It's in hibernation mode, having accomplished all of the goals and then some that were set out for it. So we're happy to now be looking at the data.
Okay. Next up is Nell Greenfield-Boyce from NPR. Nell?
Be able to explain the benefits. Oh, sorry. Just the benefits of having a manned mission to an asteroid as opposed to just collecting samples robotically.
Now, could you repeat that again, the entire question?
Oh, so I was just wondering if you could explain the benefits of having a manned mission to an asteroid as opposed to collecting samples just robotically and returning those to Earth.
I'll take that. This is Lindley again. The human spaceflight, they are still working out the objectives and constraints and requirements of a human spaceflight mission to an NEO. But with a robotic mission, you have certain capabilities that you're able to do, but since those have to be programmed ahead of time and it has to be all planned out and thought out ahead of time to get the robot to do what you need it to do, there are some limitations to robotic sample collection. One of the big advantages of humans is they're able to think on the fly and adapt quite quickly given some basic capabilities. So that would certainly be one advantage of human exploration of an asteroid, to be able to think of different things to be done while you're at the asteroid, look in different places for samples to be returned. Of course, one of the biggest science objectives of human exploration to an asteroid would be to bring back samples.
And Nell, do you have a follow-up? Okay, go ahead. She's coming. Go ahead, Nell.
New estimate of roughly 19,000 mid-sized near-Earth asteroids. The majority of those have not been discovered, and I'm wondering what missions or projects are underway to discover those. And I also wondered if you could characterize the damage to our planet that would occur if one of those mid-sized objects struck the Earth.
I guess I'll take that again. This is Lindley. Your first question is about the ongoing efforts. What are we continuing to do? We continue to run several ground-based teams that have been in operation for several years and have actually found the majority of the known objects. Those projects continue. We are looking at increased more capabilities. The NEOWISE mission kind of gave us a prototype of a space-based mission that we might look at for the future, but we have to examine the cost and benefit of doing it from space in the infrared versus ground-based observatory, larger ground-based observatories. So there's actually a whole spectrum of capabilities to be looked at. It's not one system to do it. It's a complement of both ground and space-based systems, which would probably be the best to recover the entire population of these objects. And I've forgotten your second question. Oh, thanks, Amy. You wanted some idea of what the damage of, say, a 100-meter asteroid, if it were to impact the Earth. Because of the orbital dynamics, the relative speed at which these objects hit the Earth would be on the order of tens of miles per second. So that's a lot of energy to be dissipated in an instant. So it is quite a large area that would be damaged by the impact of a 100-meter object, something on the order of a metropolitan area. If, say, for instance, one were to hit in the middle of the D.C. area, it would pretty much devastate the entire area within the Beltway.
This is Tim Spar. I'd like to make one general comment on the existing, the existing search teams. They're finding roughly 500 objects larger than 100 meters per year. And so it's a little bit slow going, but the existing assets are capable of certainly doing a good job with this.
Yeah, certainly, given enough years, they will eventually recover the population, but it will be several decades with just the existing assets.
Okay, we have one final question. I think this is a good wrap-up. This is for Amy from one of the .coms. With all this data, what are the next steps?
One of the most exciting things about having data from a spacecraft like WISE and the NEOWISE project is that there's just so many different things you can do with it. One of the things we're very interested in studying is the subset of near-Earth asteroids that are considered potentially hazardous, meaning that they have orbits that take them very close to the Earth. We're going to be looking at those in greater detail. We're also going to be studying asteroids in the main belt between Mars and Jupiter. And so we've just got a lot of good things left to do, and it's going to keep us busy for a long time.
If I might add to that, this subset of the population that Amy talks about, those that have closest encounters with Earth, that's also the population of objects which will make the best human spaceflight targets. So they're of particular interest for not just a hazard, but for exploration destinations.
Okay, that's going to wrap up here, and would like to remind folks that go to www.nasa.gov/WISE for the information presented today. Also, our participants are available for follow-up interviews. Just contact my office, 202-358-1726. Thank you for joining us. Science never sleeps.